Welcome to Math with Marty, the show where every week we amaze you with the miracles of mathematics. And it turns out that in the studios of Channel 11, there is almost no limit to the miracles that can be done on the board right in front of you. And just to show you what kind of miracles we have, the people at the studio have contrived an incredible demonstration of the magic of video technology is applied to our show, and there we are. I thought you were never going to come in with me, guys. And there we are, back as usual, and all in one piece, hopefully for the remainder of the show. And we did some very bad math last week, and it was hard math, and there is no respite for us because I am not finished with this topic, and I'm going to push it even farther. I showed solution to the cubic equation based on choosing special variables called P and Q and assuming that the solution of the cubic had to take the form of P plus Q. And we did a lot of bad stuff last week. And I'm going to take it all off the board and do the whole problem all over again in a completely different way. And the reason we want to do this problem again is because we all know how to solve the quadratic equation because you learned it in grade 11, and there's a formula for it. And in the 1500s, Italian mathematicians, and there's a dispute on priority between Cardano and Tartaglia as to who was actually the first, solved the cubic equation. The equation x cubed plus a bunch of stuff plus a bunch of other stuff equals 0. And in the same century, before the year 1600, a student of Tartaglia named Faro figured out how to solve the fourth degree equation. Actually, the fourth degree equation, you can sort of solve the fourth degree if you take something like x to the fourth plus 3x squared plus 5x plus 2 equals 0, and assume, and I've gotten rid of the x cubed component, which is always easy to do, and then all you got to do is assume that it's x squared plus ax plus b times x squared minus ax plus c, and if you multiply them out, you get a real long thing in x to the fourth and this and that, and you get complicated expressions for the a's, b's, and c's. And if you assume that those expressions have to match up with the coefficients in your original form, there's sort of a strictly algebraic way of solving the fourth degree equation. So in a way, the fourth degree, you can solve it once you've done the third degree, but the solution isn't all that illuminating. And what we want to find is solutions whose clarity of purpose and sense of meaning illustrate the way by which all equations are linked by a common form of patterns so that we could possibly understand how it is that the fifth degree equation turns out to have no algebraic solution, which was finally proved in 1831 by the Norwegian mathematician Niels Henrik Abel. And there is a proof they do in math courses, but the proof is sort of a 20th century refinement of the work done 200 years ago by mathematicians who were actually working with numbers, working with patterns, and getting their hands dirty at the ground level. The solution they teach you now in the algebra courses is so refined that you can't actually understand it, to the point where the people who teach it will tell you that the only way to understand the solution of this problem is to follow the proof in the textbook line by line, and that if you understand one line after another line, that you never achieve a total sense of understanding it all at once. The only way to understand it is to go line by line. Now this can't be right. No one does math that way. And in fact, if you look at the history of it, the great mathematicians who worked on the problem, such as Lagrange, chose as their method of attack that they should first establish a firm understanding of the way in which the second degree, third degree, and fourth degree equations were solved in order to proceed from there to see why the fifth degree could not be solved. And contrast this with the modern day approach of the university's professors who tell you that you're wasting your time looking at the third degree and fourth degree solutions, because since there's a proof that the fifth degree solution doesn't exist, why would you waste your time looking at the third degree and fourth degree? Well, I don't think it's a waste of time. Lagrange didn't think it was a waste of time, and Gauss didn't think it was a waste of time. If those professors want to continue to think it's a waste of time, let them go ahead. But on Math with Marty, we're going to do it the real way. And we're going to go back to the third degree equation. And we showed a method of solving the third degree equation last week, which turns out was the first method I learned of solving the third degree. And I tried to generalize upwards from it to see how the fourth degree might be solved. And I could never succeed. And then I found a completely different way of solving the third degree equation. And this method does generalize upwards. And therefore, I'm going to try and solve that equation by this more sophisticated technique. It's a little bit longer, but it's a beautiful method. I hope you will like it. We are looking at the equation x cubed minus 3x minus 4 equals 0. And since there's three solutions of this equation, we can rewrite this formula as x minus alpha, x minus beta, x minus gamma equals 0, where alpha, beta, and gamma are actually the three solutions of the equation. If we multiply these out by multiplication of polynomials, we get the expression x cubed minus alpha plus beta plus gamma times x squared plus alpha beta plus beta gamma plus gamma alpha x plus alpha beta gamma minus, where we see that we have the sum of the roots, the product of the roots, and a kind of combined sums and products term. These terms, which are in the form of sums and products of all the three roots, are called the elementary symmetric polynomials in alpha and beta and gamma. They're important because they represent all the basic combinations of alpha and beta and gamma in which the three roots appear with equal roles. And what this tells us is that, algebraically speaking, the roots are indistinguishable from each other. Furthermore, once we know the value of these three elementary symmetric polynomials, we can easily generate the value of any symmetric combination of the alphas, betas, and gammas. And we'll see how that works in a minute. You can see that if we compare the coefficients in front of the x squareds here to our original equation, that the x squared term has nothing in front of it because there is no x squared term in our original equation. So we can write alpha plus beta plus gamma equals 0. And I'll write that at the top of the board. Alpha plus beta plus gamma equals 0. The mixed term corresponds to the minus 3 in front of the x coefficient there. So we can write for the value of this alpha beta plus beta gamma plus gamma alpha equals minus 3. And finally, the product term, alpha, beta, gamma, represents a constant in the equation, equals 4. So I'm going to take off everything I got on the board. Just say that the equation which I intend to solve is summarized by these three expressions for the elementary symmetric polynomials in alpha, beta, and gamma. Sum is 0, mixed product is 3, and product is 4. And now let us see what we can do. We have available to us every symmetrical combination of alpha and beta and gamma, and we can generate more. For example, if we want alpha squared plus beta squared plus gamma squared, it turns out that if we square alpha plus beta plus gamma and take away two of these, then we get actually alpha squared plus beta squared plus gamma squared, which would be minus 6. It's easy to come up with these. I'm just going to write out some that we will need for further points in the discussion. It will turn out we will want the value for alpha cubed plus beta cubed plus gamma cubed, which is, I think we get that by, I think it's minus 12. And we're also going to want the value for alpha squared beta plus, I have to write this a little bigger, alpha squared beta plus beta squared gamma plus gamma squared alpha plus alpha beta squared plus beta gamma squared plus gamma alpha squared, which equals positive 12. And you can see that this is kind of a complicated expression. There is 6 little terms in this expression, and if you look at them, you can see that they represent every possible expression where 2 of the roots appear, one of them squared and the other to the first power. So we've got alpha squared beta. We should also have beta squared gamma. We should also have gamma squared alpha. And it turns out there's altogether six expressions of that form. So this is a symmetric polynomial, and its value equals 12. We can see that by noticing that it is equal to alpha plus beta plus gamma times alpha beta plus beta gamma plus gamma alpha. Take away alpha beta gamma times 3, because I'm going to have all my alpha squared betas, my gamma alpha squareds, I'm going to have all those, but I'm going to have some extra terms because I'm going to have an alpha beta gamma, I'm going to have a beta gamma alpha, so I have to take away 3 of those. This is 0, so I have 0, take away 12, because alpha beta gamma equals 4, so this should be minus 12. So there we go. I've actually got my minus signs mixed up. But I'll just fix them up because it's my show and I can do anything I want. Minus 12 is this expression and positive 12 is that expression. For now, that's going to do it for us. So let's hang on and see what we can do now. My chalk's getting a little short. I think I'm going to be burning a lot of chalk on this show, but what I got is some special colored chalk, which is a real treat for the viewers. And what I'm going to look at is taking the cube roots of unity, which are 1, omega, and omega squared, defined as usual by the 3 points equally spaced in a complex plane on the unit circle. And I'm going to take the expressions alpha, beta, and gamma and mix them up in every possible way with 1, omega, and omega squared. And what I mean by this is I'm going to take all combinations of sums and products in this way. I'm going to take 1 times alpha plus omega times beta plus omega squared times gamma. I'm going to take omega times alpha plus omega squared beta plus 1 times gamma. I'm going to take omega squared alpha plus omega beta plus 1 times beta plus omega squared gamma.
Omega gamma.
Thank you, Neil. And notice that these 3 terms are all sort of rotations of each other. If I multiply this one by omega, I get the second one. If I multiply the second one by omega, I get the third one. Then there's another group of 3, which I'll just space by a line, which constitutes different rotation, where I take 1 times alpha plus omega squared times beta plus omega times gamma, and the rotations of that, which will be omega alpha plus beta plus omega squared gamma, omega squared alpha plus
omega beta.
Thank you, Neil. Omega beta plus gamma. And it's interesting that if I can find values for all of these 6 expressions, if I add them up, a miracle happens and alpha becomes isolated. That's not quite true. what I should really say is I'm going to be taking the cubes of all these expressions. And when you cube all these expressions, since they're only rotations of each other that they're multiplied by omega, they all have the same cube. So really these ones aren't going to bother me. And same with these. They form a group where they all have the same cube. In other words, these represent 3 cube roots of the same quantity. So let's just get rid of them. Now it turns out I only have two expressions to worry about. If I can solve for these 2 expressions, then the problem will be solved, because if I add these 2 things together, alpha becomes isolated. Actually, it adds up to 2 alpha plus omega squared beta plus omega squared plus omega gamma. But since omega plus omega squared on the unit circle adds up to -1, the value of this expression becomes 2 alpha minus beta minus gamma. And using the identity alpha plus beta plus gamma equals 0, this equals 3 alpha. So if I can find these mixed products, then the problem will be solved. So I'll return to the task of finding the value for this expression. And let's see how we do it. What we got to do is take the cube of this expression, and when we do, we get alpha cubed plus beta cubed plus gamma cubed plus 3 times omega times alpha squared beta plus beta squared gamma plus gamma squared alpha plus 3 omega squared times alpha beta squared plus beta gamma squared plus gamma alpha squared plus 6 alpha beta gamma. And once we get to this stage, a lot of this stuff turns out to be symmetrical in alpha, beta, and gamma. And once you get something symmetrical in alpha, beta, and gamma, something you can get rid of because it's something that has a number associated with it. So all these things become known quantities. I've got, let's call this thing P. P cubed equals, I've got P cubed equals alpha cubed plus beta cubed plus gamma cubed, which from my earlier identities was 12. 6 alpha beta gamma is 24. And then I've got a bunch of stuff in these mixed up terms. Well, I'll just write, there's a bunch more terms left, multiplied by omega, and a bunch more stuff times omega squared, which is also a bunch more stuff. And what you got to do now is everything that turns out to be numbers, you bring it back over to the left-hand side of the board, which gives us P cubed take away 36 equals 3 omega times alpha squared beta plus beta squared gamma plus gamma squared alpha plus 3 omega squared times alpha beta squared plus beta gamma squared plus gamma alpha squared. And what's going to happen later, I'm going to take this expression and square it, and I'm going to take the stuff on the right-hand side, I'm going to square that stuff too. And when I square it the second time, everything that is non-symmetrical will become symmetrical and therefore will have actual numerical values associated with it. you can see that the stuff I've already got is already more symmetrical than the stuff I started out with. I started out with stuff like alpha plus omega beta plus omega squared gamma, which was mixed up in alpha, beta, and gamma. And I've got it down to the worst thing I've got here is alpha squared beta, beta squared gamma, gamma squared alpha. It's almost symmetrical, but it's not fully symmetrical because it lacks this other part, alpha beta squared, beta gamma squared, and gamma alpha squared. But when I square it all together, it will become fully symmetrical. And we'll see how that looks in a few minutes, but first we're going to sit down and do a song. With any luck, we may not even see that at all. What do we got, guys?
Well, I guess we're going to try singing that Captain Mateo song.
We should introduce our guest, musician James Meagher, who is with us just like last week. He's going to put in some harmonies and do a little guitar picking. And it's a pleasure having you on the show.
Nice to be here.
Remember the words, Neil?
No.
Damn. After that, no one wants to see any more math, do they? I can't square that. Do you think I can square that? I can't. No, actually, I could do it if I really wanted to.
You just kind of file a little bit off one end?
Yeah, just around the corner. Yeah. I could take the square of that thing. The thing is, if you did square it and everything turns out to be symmetrical, and it does, you end up with p cubed take away 36 squares equals some kind of number. And then you pull the number over to the other side and you start taking square roots. You take the square root and then you get the square root of that. And then you add 36. And then you take the cube root of that. And you get that p equals a bunch of actual stuff. But you don't want to see that. I want to do another song. North to Alaska, go north, the rush is on. North to Alaska, go north, the rush is on. Big Sam left Seattle in the year 1902 with George Kraft, his partner, and brother Willie too. They crossed the Yukon Valley in the land of the midnight sun. Yeah, Sam McCord was a mighty man in the year 1901. Where those rivers are winding, big nuggets they're finding. North to Alaska, go north, the rush is on.